see, it's the interaction between both the subsurface temperature and current flow characteristics in the atmosphere that's actually going to have quite a profound effect on the climate, tropical rainfall, precipitation, pressure variation in this part of the globe. However, as we'll see, it will also impact winter weather patterns in the mid-latitude regions of both hemispheres, and potentially it can also influence the global mean temperature as well. So it's very important to understand the circulation patterns in this part of the globe. So this picture here shows the typical average sea surface temperature during those different months of the year across the Pacific, between plus or minus 20 degrees of the equator from the west to east part of the Pacific. And the thing to take away, the message to take away, is that the mean state of the tropical Pacific Ocean is going to be characterized by both its surface temperatures, or sea surface temperature, SST, but also we have to remember what's going on just below the surface as well. In other words, what's going to happen to the thermocline as we move from this part of the Pacific to this part of the Pacific. And it's the type of that thermocline that can be quite important for eventually characterizing the atmospheric interactions as well. So remember, on average throughout the year, you can see that the water tends to be warmer in this part of the Pacific compared to this part of the Pacific. And we alluded to that when we talked about the Vocals field experiment. So remember, typically much warmer this side of the Pacific, typically significantly cooler on that side of the Pacific. And when we say we're talking about cold water here, if you look at the scale, at these equatorial regions, cold is 18, 19, 20 degrees centigrade. Warm is 27, 28, 29 degrees or even higher. So much warmer on average than, say, extratropical mid-latitude and northern latitude sea temperatures. So remember, warm water is going to expand, and that means, of course, that the sea levels in this part of the Pacific is going to be significantly higher. It also means that the thermocline is going to be much deeper, because remember that mixed surface layer of the ocean, it's actually going to be much deeper here compared to this side of the Pacific. And that gradient is very important for what's going to happen in terms of the subsurface currents. Now, the height variation, which we just mentioned, is actually going to drive an ocean water flow from this side of the Pacific to this side of the Pacific. And we'll see a figure showing that later. And of course, remember, if we're going to get a flow up this much deeper thermocline to a much shallower thermocline up here, that's actually going to be a flow in the opposite direction to the surface winds, which, remember, when we talked about the Hadley cell, we're going to have these essentially easterly winds along the equator. So one would normally expect those easterly winds to drive a surface current in this direction, and it does to some extent, but really that's going to be confined to the thermocline or mixed layer region. Now that reverse current flow beneath the surface, beneath the thermocline, is going to occur at around about 100 meters depth on average. So when we're talking about subsurface currents, that's the sort of average thermocline depth we're going to be thinking about. And of course the ascent, as we move from this side of the Pacific to this side of the Pacific, is going to result in, of course, much cooler water from below the thermocline, and that, of course, is going to be very nutrient rich. And of course the fishing communities in that part of the world are familiar with this cycle, because of course it benefits the local fish populations and it benefits them. So they're actually quite familiar with this so-called Pacific Ocean circulation, because it affects their livelihoods. So remember, we have the Hadley cell, those two thermal belts about the equator, producing this convergence of surface flows along the surface. But remember, we also have this high-level westerly zonal flow as well between those two thermal belts. And on the other side of the Hadley cell belts, of course, we've got the so-called Ferrel cell, the mixing zone, and that interaction between that cell and the Hadley cell, plus the interaction with the polar cell, is going to produce these wave-like patterns. And as we'll see, the temperature gradients in the Pacific are also going to influence the shape and magnitude of these wave-like patterns, these Rossby waves, which are going to influence the weather and climate in North and South America. Okay, so this is a 3D schematic of what we've just been talking about. as we said, the ocean surfaces temperatures across the Pacific are going to contribute to the observed patterns of tropical rainfall and also tropical thunderstorm activity, as we see there. Typically, where we see the strongest heating of the sea surface, we're going to get most precipitation, most thunderstorm activity. And typically, we tend to see most rainfall and thunderstorm activity across Indonesia and the western tropical Pacific on this side of the picture here. And of course, because of this very strong heating at the surface, it means that this mixed layer down, which defines the depth, if you like, to the thermocline, is much deeper. Whereas on that side of the Pacific, of course, you've got much cooler waters, less convection, and of course the thermocline is much shallower. We tend to refer to this thermocline as the equatorial thermocline to differentiate it from the previous thermoclines we've been talking about. So, what happens when we get this strong ascent in this side of the Pacific? Well, of course, we're going to reach the tropopause. We're going to get the air essentially trying to flow outwards again when it reaches that very strong temperature gradient. Now remember, we talked about the Hadley cell circulation transporting air polewards. This is different. We're also going to get this upwelling air now meeting that strong westerly zonal flow across the top of the Hadley cell. So we're going to get air transported across the Pacific with those westerly winds. It's going to cool, it's going to descend on this side of the Pacific, and that's going to cause slightly higher pressure when it descends here. And of course, that descending air has to flow out again, and it's going to meet up with the convergence zone down at the bottom here, producing, contributing to these easterly flows as well. So what we've got is another atmospheric circulation pattern. And this is what we typically see, for example, in December, February. And these are what are called the normal conditions for the so-called Walker circulation. So this Walker circulation is the key circulation pattern defining flow across the Pacific region. So remember, highest rainfall on this side of the Pacific, lower rainfall on that side of the Pacific. And if you think about it, depending upon the gradient of the sea surface temperature and the depth of this thermocline, that's going to control to some extent where the maximum precipitation is going to occur. Okay. So, where do we go from here? How is that pattern going to change? We said these are normal conditions. What happens if that thermocline depth changes? How's it going to affect the Walker circulation pattern? Well, those are the topics we just went through, so make sure that you're familiar with those initially. So if somebody asks you what the Walker circulation is, you can explain briefly what the key characteristics are. So let's keep going now and think a little bit about what effect the equatorial heating is going to have on those wind patterns. Now, normally, the strongest heating of the sea surface temperature and the associated air temperatures above are actually going to coincide with the warmest ocean waters and the heaviest precipitation, as we'll see. And not only that, that atmospheric heating is actually going to determine the north-south temperature gradient in both hemispheres. So what we have here is the January-March mean ocean temperature, similar to what we saw before, compared to the mean ocean temperatures in July-September. In other words, the one on the left is the northern hemisphere winter, the one on the right is the southern hemisphere winter period. And let's look at what happens to those high-level winds, or jet streams, and this shows the contours of wind speed in meters per second measured at a pressure level of 200 millibars, those high-level winds. And what you can see is that the jet streams seem to be a maximum between 20 and 40 degrees north in the January-March period and extend beyond the international dateline, 180 degrees there. Whereas if we look at the southern hemisphere winter period, you can see that the jet stream is now a maximum on this side of the equator, between 20 and 40 degrees south. And of course, the strength and the eastward extent of those jet streams is going to control the airflow that goes into North America and Canada in this particular part of the globe, whereas in the July-September period it's going to control the airflow moving into South America. In other words, the sea surface temperature heating and the grading is going to control the winter weather patterns in the northern and southern hemisphere in those continents. So that's why it's so important and why we need to try and predict what's going to happen. So remember, those jet streams are a major factor controlling the winter weather patterns and of course the storm tracks in the middle latitudes over the North and South America between 20 degrees and higher. Right, so how do those temperature gradients change? Well, of course, they're not constant. We just showed some average values in those previous figures, but they can vary significantly from year to year. So it's important to understand how they can change so we can make forecasts for the year ahead. One can imagine that if we have higher rainfall in certain regions or less rainfall, that's going to have significant impact on communities. So let's have a look at some of what we call the different extremes of the so-called El Niño Southern Oscillation, or ENSO. We'll define that in a moment. And these variations are incredibly important because their impacts are huge. The changes in temperature, as you can see, actually extend more than a quarter of the circumference of the globe, but their knock-on effects on precipitation, pressure and weather patterns can extend to more than half the circumference of the globe, and they can affect global mean temperatures as well. So there are two phases to this so-called ENSO, or El Niño Southern Oscillation. The so-called warm phase, or warm Pacific episode, or simply ENSO, is actually called El Niño, and the so-called Pacific cold phase, or La Niña, is shown on the right-hand side, and I think you can see immediately what the differences are. El Niño episodes represent essentially periods when we get abnormally warm water stretching all the way across the Pacific into the eastern tropical Pacific, as you can see on the left-hand side there. So the temperatures in this part of the Pacific are above average. La Niña is sometimes referred to as the other extreme of the ENSO, but the word extreme is not typically used because we're dealing with non-linear effects here, but you can think of it as a sort of the flip or reverse of El Niño, if you like. And those, of course, are periods when we get much colder sea surface temperatures on the right-hand side of that picture near the coast of South America. Now, during El Niño periods, the sea surface temperature in that part of the Pacific can be between 2, sometimes up to 5 degrees centigrade higher than average. Whereas during La Niña, the temperatures of the sea surface temperatures in that part of the Pacific can be between 1 and 4 degrees C lower than average. So remember, during strong El Niño events, which is shown here, this is an example in January-March 1998, the temperatures are much more uniform across the globe, and that one on the right is strong La Niña from January-March 1989, the temperatures are much cooler. And the bottom graphs here shows one way of diagnosing whether we've got an El Niño or La Niña. So you can take an average sea surface temperature based on the previous graphs, subtract this particular year, the period January-March, the sea surface temperature from those, and then you get these so-called ocean temperature departures. So again, this simply shows that to the right-hand side of the international dateline here, you have much warmer waters based on these temperature contours, whereas during La Niña, you tend to have much colder waters on this side of the Pacific. So, those are the key features I want you to try and go back and read about later when we're talking about ENSO. Be able to identify the difference between El Niño and La Niña, and remember, due to the non-linear response, some people will tell you that La Niña is not really just the opposite of El Niño. There are strong non-linearities in those sorts of feedbacks and interactions which make it much more complicated actually. So, Those are the key features. Please read those and make sure that you understand the differences between El Nino, La Nina, and what the key differences are. It doesn't just affect, obviously, the sea surface temperature. We basically said it also affects the ascent and descent of air, and of course that means it's going to affect pressure. And what we see here is a typical pressure at the sea surface based on a strong El Nino event versus a strong La Nina event, the same as those previous ones. So those fluctuations in ocean temperature are going to be accompanied by these very large-scale fluctuations in air pressure, and those are what we actually refer to as the southern oscillation. When we talk about oscillations in the atmosphere, we're normally talking about pressure perturbations. So during El Nino, you get a normally high pressure covering Indonesia and western tropical Pacific, and much lower pressure covering the eastern tropical Pacific. So remember, those are pressure departures compared to the average. So during El Nino, you tend to get higher in that part of the world and lower in that part of the world. Whereas during La Nina, you get a normally low pressure over Indonesia and the western tropical Pacific. And that's, as we'll see, due to the patterns of convection which can stretch further across the equator in El Nino versus La Nina periods. And this is just a picture showing the difference between El Nino and we'll see later La Nina. So remember, during El Nino, because we get this strong warming of waters all the way across the Pacific, we have much deeper thermocline on this side of the Pacific, which tends to restrict any upwelling, so any upwelling is much weaker. Remember, we have the trade winds moving in this direction from the Hati cell, but of course, because we're now producing precipitation and thunderstorm pretty much all the way across the equatorial region into the central Pacific, what we tend to see is that that uplift, when it meets those zonally averaged mean flows at high levels, tends to weaken the Walker circulation. And in fact, sometimes you can even get reverse flow at high levels, depending upon the strength of those thunderstorms. So this flow tends to essentially weaken the trade winds at the surface, which effectively means that you weaken the Walker circulation overall. But sometimes you can even get westerly winds moving in this direction at the surface. And one of the things we didn't mention, of course, is that those surface winds also affect the circulation patterns of water currents within that mixed layer, the thermocline. So normally when you get these trade winds, it drives these fairly weak surface water currents in this direction, as you might expect. But of course, if we've got a very deep thermocline all the way across, we also tend to get outflow from the coast here, which tends to restrict the circulation pattern within the thermocline. So remember, El Nino, periodic warming of the central and eastern equatorial Pacific, offshore from Ecuador and northern Peru, typically between 5 degrees north and 5 degrees south latitude, and between about 170 and 120 degrees longitude. And of course, what that means also, because we've got this strong convective activity here, is we tend to get more precipitation than the Central Pacific as well during El Nino. Whereas during La Nina, we have a stronger gradient of that, in that thermocline, stronger upwelling, and we also then tend to reinforce the Walker circulation. So that tends to enhance the surface winds or trade winds in this during those sorts of periods. We tend to get more precipitation confined to this side of the Pacific. And of course, because most of the ascending air is confined to this part of the Pacific, we tend to get an average lower pressure here compared to higher pressure from descending air over there. Now remember, of course, we're also going to get higher sea levels on this side of the Pacific. It's kind of hard to see from this diagram, but typically we're talking about maybe roughly a half a metre higher on this side of the Pacific. It may not sound like much, but it is significant in contributing to that upwelling flow that you can see there. Okay, so again, go through those points, make sure you understand the interactions we just talked about, and also try and understand how those airflows we just talked about is going to affect the Walker circulation. So warmer water confined to the Western Pacific Ocean is going to push back eastward due to the weakening trade winds, as we see in this little animation. Sorry, it's very short. And we can use that information, as we'll see, to actually try and predict what's going to happen in the coming year. And there is, in fact, a so-called Climate Prediction Centre, CEC, which monitors and predicts when we're going to get an official El Nino event based on 3-month average sea surface temperature departures. And the official definition is when we get a departure from the 3-month average sea surface temperature of more than half a degree, then that is going to be defined as an official El Nino event. So, based on everything we've talked about, this shows the sea surface temperature measured by a variety of techniques. We'll mention those in a moment. And this shows the sea surface temperature variation across the Pacific from 12th of December 2018 through to the end of February 2019, so not so long ago. So, let's just see how it changed over those periods. And I want you to ask yourself, well, if you were a member of the CPC and knowing what you just heard, would you say that 2019 is going to be an El Nino year or not? So let's see how the sea surface temperature varies as we go through to the end of February. So, do you think 2019 is a La Nina or El Nino year? Somebody says El Nino. Why? It's all right guessing yes or no, but you have to say why. Okay, well, have a think about it. You're correct. Effectively, the forecast is that climate warming El Nino is very likely in 2019, says the United Nations agency responsible for making those announcements. So, monitoring the sea surface temperature is very important for defining when we're going to have an El Nino, because that is going to help us forecast where all this precipitation is going to occur, whether we're going to get floods in one region versus droughts in another region. So how do we actually make those measurements? Well, we use a number of different platforms to monitor the sea surface temperature, but also the subsurface temperature, which actually turns out to be slightly better for predicting El Nino. So we use satellites, obviously, as we talked about earlier in the course, effectively, to measure sea surface temperature when there are no clouds in the way generally. But we also use the satellites to actually relay data from a whole range of measurements across the Pacific. So along the coasts on either side of the Pacific, we have these tide gauge stations for measuring the height of the sea, but also the temperature and current flows. But then you see these little yellow dots all the way across the Pacific, stretching about plus or minus 20 degrees south, where we see the maximum temperature variation. Those are what we call moored buoys, and they measure the meteorology, the wind speed, temperature, relative humidity, but they also measure sea surface temperature as well. So you can see that those are stretched all the way across the Pacific, and they telemeter the information to satellites, which are then transmitted to various data centers around the world to look at the data, process it, and make predictions. Also, we have these so-called drifting buoys, which essentially move with the sea surface currents, measuring the air temperature, sea temperature, etc. Knowing their position, we can measure the speed of those currents as well. Then, of course, we have lots of volunteer observing ships which have meteorological stations on them, but also measure sea surface and below sea surface temperatures as well. So all this information from all these different sources has to be brought together to produce the graphs we saw previously. Now, over the last 100 years or so, the way we tend to identify some of these big atmospheric perturbations due to the change in heating across the Pacific have resulted in several different so-called indexes to identify whether we're going to get an El Nino or La Nina. And one of the earliest was called the Southern Oscillation Index, or SOI. It's not used so much now for predicting, but because it's the oldest, it's still very useful for looking at historical changes in El Nino, La Nina events. There are quite a lot of these new indexes available now because of all the new data we have available. For example, we have the Equatorial Southern Oscillation Index, which started around about 1947. Then we have the Low-Level Wind Index, the Upper-Level Wind Index, outgoing long-wave radiation, a proxy for tropical precipitation. And then there's a newer one, which is called the Ocean Nino Index. But the Tahiti-Darwin Southern Oscillation Index is the oldest and still referred to. So, what is the Tahiti-Darwin SOI index? Well, actually, it's the difference between the atmospheric pressure at sea level at Tahiti and at Darwin. Actually, it's the difference in the pressure anomaly. So, way back in the 19th century, when these measurements were first started, there were effectively only two stations in this part of the world, one at Tahiti and one at Darwin. So, during an El Nino event, it was noticed that the pressure is below average in Tahiti and above average in Darwin. So if you subtract those differences at Tahiti and Darwin, the Southern Oscillation Index, or SOI, is negative. Now during La Nina, the opposite is true. It becomes positive. So there's this long-term time history of pressure at these two sites, which we can use to try and indicate, look to see whether we got El Nino or La Nina events. But you can see immediately there's a problem with that SOI. Look at the locations. Tahiti is about 18 degrees south and Darwin's about 12 degrees south, and there's only two stations. And the problem is that if you just simply subtract the pressure anomalies, you can get interference from non-ENSO events, mainly daily and weekly weather patterns, etc. So what you have to do is you have to take 3 monthly averages, which tends to make the information less useful for predicting El Nino and La Nina events. The other problem, of course, is that they are significantly south of the equator, where most of those changes we talked about take place. Remember, we're actually getting close to the plus 20 degrees south versus the equatorial region here. So they're in a slightly wrong place, so they don't give us quite the strongest signal we would like to look at the El Nino, La Nina events. However, to get round that, a more modern index was put together called the Equatorial Southern Oscillation Index. And that's shown here. So it took a number of stations in this region here over Indonesia and a number of stations and ship measurements over the eastern Pacific, right on the equator. So you compare the pressure perturbations from those two different regions. However, the data from the so-called ESOI only goes back to around about 1949, whilst the Tahiti SOI index goes back to the late 1800s. So you get much longer station records. So, due to its longer records, the Tahiti-Darwin SOI is actually still used to represent ENSO in historical data sets and to compare with more modern data sets as well, just to look at the frequency and the cycles of these events. And if we actually look at the Tahiti-Darwin SOI index, you can see here how we interpret them. So the top graph shows the ocean temperature departure based on a running mean compared to an average. So typically you use 3-month averages. And what you can see from about the late 1960s up to just before 2000, you can see the temperature departure between 5 degrees north and 5 degrees south over the region 170 and 120 degrees west. And of course, where we see prolonged periods of the SOI value, which is shown below, then we tend to get abnormally cold sea surface temperatures. This is the Tahiti-Darwin SOI using a 3-month running mean. Where we tend to see abnormally low pressure, we tend to see that corresponds to higher surface temperatures. So the difference between the air pressure anomalies at Tahiti and Darwin, a negative number indicates below average air pressure at Tahiti and above average at Darwin. And of course, this corresponds to El Nino, this corresponds to La Nina. So, what can we say about that particular pattern? Oops. That we see there. Can you see any periodic pattern at all? Well, let's go through and see what the basic features of that time series is. The negative phase of the SOI represents below normal air pressure at Tahiti, and above, as we said, normal air pressure at Darwin. Prolonged periods of negative SOI coincide with abnormally warm ocean waters across the eastern tropical Pacific, typical of El Nino episodes. Prolonged periods of SOI values coincide with abnormally cold ocean waters. But do we see any patterns? Well, if we have a look carefully, you can see that the period seems to average around about 4 years. However, there's a lot of variation, typically from about 2 to 7 years. The 1980s and 90s, as it says there, featured a very active ENSO cycle. We had 5 El Nino episodes and 3 La Nina episodes in that short period. The period also featured 2 of the strongest El Nino episodes of the century, as well as 2 consecutive periods of El Nino conditions during 91 and 95, without any intervening cold period. It was very quiescent between those two. So, historically, you have to remember there's this considerable variability in the ENSO cycle from one decade to the next. There are decades when the cycle is very inactive, and then decades subsequently when it's very, very pronounced, which makes it difficult to predict. So, that's the patterns that people look at using more modern southern oscillation indexes today to try and predict whether we're going to have an El Nino or La Nina year. And indeed, this was the old lecture from 2015 where they actually showed this picture of the evolving sea surface temperature during 2016, and again you can see that was another El Nino period as well. Now what we can do with that information is essentially get that red dot, which is an average from November, December, January in 2015, corresponding to that previous animation, and we can then put it into a very complex coupled ocean atmosphere model and try and predict what the sea surface temperature is going to do over the following year. So this is the target season for the computer model, and you can see the red are the actual observations, and in light green is the best estimate from the computer model with some uncertainties either side, as you can see. So that model was predicting El Nino with some uncertainty. Now, probably just as important as the pressure is, of course, the precipitation that we expect during these different phases of ENSO, particularly during El Nino. So as we said, during El Nino we get this very strong thunderstorm activity developing across the equatorial Pacific in regions where we tend to get abnormally high sea surface temperatures compared to the average. And what does that do to the precipitation? Well, this graph here shows the total precipitation. The units are not particularly important, millimeters. And what we tend to see is, for example, during January, March of this particular event, 1998, we tend to get quite high precipitation much further west, but also extending beyond the international dateline into the Central Pacific compared to a more quiescent period during El Nino. If you look at the departure, in other words, the difference between this precipitation and the typical average, you can see that we tend to get actually lower precipitation over Indonesia, Philippines region up here compared to here, because a lot of precipitation has moved into the equatorial Pacific. And we tend to get more over that side of the Pacific. That may not look like very much, but that can basically cause droughts in this particular part of the region. Whereas over here, on this coastal region, you might also expect to see enhanced precipitation, perhaps even flooding, depending upon the topography of the local continent there. So, further west, rainfall tends to be suppressed across Indonesia and Philippines, but also northern Australia. During La Nina, convection is greatly enhanced over the Indonesian region, and we tend to get drier conditions prevailing near the international dates region because we compress all that convection to this side of the Pacific where most precipitation normally occurs. And just to show you, this is what happens during La Nina. During La Nina, the rainfall and thunderstorm activity is going to diminish over the central part of the Pacific. You can see over there the departure in brown there, so you tend to get negative values there, whereas very close to this side of the Pacific you tend to get a bit more. And of course if you tend to get a bit more, which is the green, you tend to get flooding in those regions. So it's very important to be able to predict El Nino, La Nina events in order to predict whether we're going to get more or less precipitation and hence drought or flooding. One important point, is that the area experiencing a reduction in rainfall generally coincides very well with the area of abnormally cold ocean surface temperatures. So the sea surface temperatures are actually quite useful for helping to predict whether or not we're going to get more or less precipitation. So, again, this is just to remind you, this is the water circulation during El Nino, where we have this fairly deep mixed layer, not a very strong gradient in the thermocline. It's reduced or near zero across the entire Pacific. We get reduced upper level wind speeds, that weakens the water circulation, more precipitation all the way across the Pacific. We get reduced surface wind speeds as a result because of the outflow from those different regions of thunderstorm activity, perhaps even generating westerly flows contra to the surface easterly winds. And of course we get a higher sea surface height in this part of the Pacific. So those are the main features you should try and remember, and then try and link them to the weather patterns, and also remember the difference between that and La Nina conditions, where we have much stronger circulation, increased surface winds. In other words, we enhance the water circulation, more precipitation, higher temperatures on this side of the Pacific, much cooler temperatures on that side of the Pacific, much deeper, much stronger gradient in the equatorial thermocline. Okay, so of course this is going to have an impact, as we said, because of the way it affects the position of the various zonal jet streams. And this is just a summary of some of the impacts that El Nino has, in other words the warm episode period, has on weather patterns. And this shows the typical influence during a typical December-February period. So they're the strongest, remember, in the northern hemisphere during the boreal winter, when the water temperature reaches its annual maximum, all the way across the Pacific. Above normal temperatures of the water associated with those events redistributes convection, and that induces those changes we saw in the jet stream behavior north of 20 degrees. Whereas south of 20 degrees in the austral winter period, the impacts of El Nino are much weaker and confined to the southern hemisphere. But the knock-on effects are we tend to have warmer weather conditions in certain parts of North America and Canada, and wetter and cooler weather in the southern states of the United States. Now, I just want to summarize, there's quite a lot of different features on that graph. I just want to summarize the key components. So what happens during El Nino episodes? What are the main things that occur, and how does it affect the atmospheric flow and the weather patterns? So this is just the main ones, not all of them. So what tends to happen during El Nino episodes, we get a flattening of that mean wave pattern, those big Rossby wave patterns we talked about earlier last week. That means we get a much more zonal flow without any of those big waves going across the northern Pacific. And that means that effectively that we get more normal flow, if you like, going across the eastern North Pacific and North America, rather than these big waves which can lead to blocking, etc. We also see during El Nino, remember, a pronounced eastward extension and equatorial shift of that East Asian jet to the southwestern United States of America. And along with that flow pattern, we get these mid-latitude low-pressure systems, which tend to be much more vigorous because they're moving faster than normal over the eastern North Pacific and the southern United States. And that produces actually much more stormy weather during that winter period, and we get more precipitation, for example, across California and the southern United States. So it's cooler, windier, etc. in that part of the United States. But there's also an enhanced flow of marine air into most of North America because we've got this stronger zonal flow without these wave patterns. And that means we get a reduced northerly flow of cold air coming down from Canada, from the polar jet and the polar cell, the United States. that means you're actually going to get milder than normal winters across the northern parts of the United States and western Canada. So the implications for ENSO are very far-reaching. What about La Nina? Well, again, please go through these graphs on your own. This shows, for example, the December-February cold episode relationships, and also one for June-August. And you can see you get very different patterns in terms of the weather impacts, in terms of cool, dry, wet, cool and wet weather, particularly over North and South America. So again, let's just look at the key features. La Nina episodes feature 3 prominent changes in the atmospheric flow across the North Pacific and North America. Instead of actually flattening that zonal flow, those big waves, we actually amplify them. Because of the way La Nina works, we tend to get all the convection on one side of the Pacific, so that actually leads to an amplification of the so-called climatological mean wave pattern. That also tends to increase the meridional flow across the continent and the eastern North Pacific. Because we've got these big waves now, that tends to lead to what we call blocking activity across the eastern Pacific, eastern North Pacific. That means we get this highly variable jet stream strength over the North Pacific, eastern North Pacific, sorry, and the mean jet position, which is key to controlling the weather patterns in North America, that can actually enter mainly through northwestern United States and southwest Canada. Also, we have these large parts of central North America experiencing increased storminess as a result. More precipitation, increased frequency of significant so-called cold air outbreaks, particularly from the polar regions, which are now allowed to descend from the Canadian region. In contrast, the southern United States experiences less storminess and less precipitation. There also tends to be much more variability in the month-to-month changes in temperature, rainfall and storminess across central North America during the winter and spring seasons as a result of those changing circulation patterns. So go through these and make sure you understand the basic changes. There are lots of other ones, far too much detail than we can go into in this course, but make sure you understand the basic changes that are influenced by ENSO, El Nino, La Nina during the through the northern and southern continents of the Americas. And this graph here just summarizes what we've been talking about. So El Nino, we tend to get the polar jet stream moving much further north and to the east, whereas we have much warmer weather leading to wetter weather in the southern United States and drier in the western United States. Whereas La Nina, we tend to have these big wave amplifications, a much more variable Pacific jet stream, and also the polar jet stream can then enter much further south, producing wetter, colder weather, much more variable weather, but that leads to drier weather in this part of the United States. So all these interactions have to be predicted as best as possible. Finally, there is another way you can actually look at El Nino and the impact on precipitation. Now these are what are called Hofmöller diagrams. So what we see here essentially is the year and month on the vertical and the latitude across the Pacific shown here. In the first diagram, we actually see the sea surface temperature. These are actually departures. It should say departure somewhere. It doesn't. Sorry about that. And over here we have the pressure near the surface, around about 850 millibar, wind speeds in meters per second, and over here we see the precipitation in millimeters per day. And it turns out that you can see that, well, these are the key features. During El Nino, where we have this enhanced water temperature, as you can see, for example, on the top of the first diagram, we have these abnormally high temperatures, and we also have easterlies as well. During La Nina years, rainfall is suppressed, where water temperature is lower than normal, and easterlies are much stronger than normal, based on those wind speeds in the central figure. The relationship between sea surface temperature and those wind speeds and precipitation, however, do vary. The strengths of the relationship vary from event to event. And because all these anomalies, as they're called, develop contemporaneously, it's actually not quite that useful for forecasting. turns out there's a slightly better thing you can do, and that's actually to use the thermocline depth. That seems to be a much better indicator, as you can see here, where we have much stronger correlation between the precipitation and the ocean subsurface temperature where the thermocline exists. And you can see where we have these very strong temperature increases, we have these big increases in precipitation, or we have big decreases in temperature, we have a big decrease in precipitation. So that thermocline depth turns out to be as useful, if not more useful, indicator or predictor of El Nino and La Nina events. This is all part of ongoing research to improve current models to predict El Nino and La Nina. So I think we've finished with ENSO. This is just a summary of what we've been talking about for the last couple of days. So make sure you understand these basic overview points in terms of the behavior of ENSO, how it links to the wind patterns, how it links to the sea surface temperature, the pressure perturbations, the thermocline depth, and the potential or the knock-on effects on the weather patterns in the northern and southern hemispheres, particularly over North and South America. So remember, sea surface temperature evolution, El Nino, La Nina states are the sort of flip parts of the ENSO. Sea surface temperature distribution, thermocline variation is very important. The impact precipitation distribution, and of course sea level pressure anomalies as well are also affected. And we can use that for looking at historical El Nino, La Nina events. So that's all we need for this course as far as ENSO is concerned. Well, for those of you who are interested, ENSO is not the only oscillation across the Pacific. There's also another one called the Pacific Decadal Oscillation. That was actually only identified in 1996, so we're still learning a lot about it. So if you're interested in that, then there are a couple of slides which actually explains the different phases of the so-called decadal oscillation and why it might be important for long-term prediction of climate. But don't worry about that for the examinations at all, only if you're interested. Okay, tomorrow we're going to start looking at radiative forcing and evidence of climate change. Thank you very much for coming.
For next 20 minutes?
I have to get to a tutorial now.
I analyzed the size result data. The experiment worked. I put the inlet sheet of wind directly 2 centimeters to the axis of air pressure.
Okay.
And there is a size result.
You have a graph?
Not really. You can just on one side. This one is
So these are all at the same distances. What I suggest you do is essentially reorder these so that you have all the ons, take an average and standard deviation, all the offs, take an average and standard deviation, and plot the average of all the ons versus size and all the offs versus size. Have you done that?
I have done a similar thing, like this is the first 30 minutes.
Is this size?
No, it's a time field.
Okay. What I want to see, well, speak to Professor Cole, he's doing that for you. So, take that on, that on, that on, that on, that on, average it for that size, and produce the standard deviation, lovely one for here obviously. Do the same thing for all the other channels. So that's for on. So is that for going into or coming out? What do you mean by on off?
I put the inner tube, the exit of the.
So you've got the filter
Yeah.
blowing out and you put the inlet tube, so that's on.
Yeah.
And then what you did was you
Switch this off.
switched it off. Okay, that's fine. So do that, and then do the same thing for off.
Yeah.
Now you can put those on the same graphs.
Yeah.
So you might expect there to be, if it's working, it might not be working, you would expect when you put the graph on there to be less particles coming out. Now when you say n, this has to be total.
Yeah.
So what I'm asking you to do is comparing what's essentially in the room compared to what's coming out. Is there a difference? What is that difference?
That's just the thing from
Now, if you look at on, sorry, background,
this on.
so when you turn it on, you get, I'm not sure what this number is. Why is this so big?
This is the launch time, I think.
Okay, this is 13, yeah. That's the problem. The background is varying, isn't it?
And the 3 o'clock there is a fire alarm.
Yeah, when I was thinking of on, off, I was thinking of doing it for 2 minutes, 2 minutes, 2 minutes, 2 minutes, to compare what goes in and comes out with a fairly constant background. Your problem is that your background is changing quite a lot.
I'm trying to say this purifier is too weak to distinguish it from the background.
Do those graphs anyway, it might show something. For example, if we were to compare, where would we have two that are very close together? Because we don't have two that are close together.
Like a 15-minute cycle.
I'm thinking 2 minutes, but you've got it. You've got the raw data, have you?
Yeah.
So this was on continuously for 5-6 minutes, or off for 5 or 6 minutes. So you took it off,
Yeah.
and then you kept it off for until 15:11,
Yeah.
or rather, sorry, for 14:40, 56. So you have the raw data between there and there.
Yeah.
So you can calculate a standard deviation with time. So there will be standard deviations associated with
You
each of
mean
those.
2 minutes before?
Yeah.
Okay.
What we're trying to do is see whether or not the background is different to the what comes out. So you start out with 590, you immediately switch, and it does go down quite a lot. So that's the first graph, I would say. Forget about doing the averages for everything. I hadn't realised that the times were so different. So that's the first one. Then you put it back on. You could do a graph comparing that one and that one. And the slight problem is that the background's changed.
But the problem is this air purifier claims to deal with fungi and bacteria, so we should look at fluorescence.
Yeah, but you still have to make sure that you've got the total sorted out, because it will also remove total particles, not just fungi and bacteria.
Yeah,
Okay. Okay, well let's leave that one then. Do what you can with those graphs.
Yeah.
Let's see. So what you could do, I suppose, is again do this, but do it for do an average of all these that are on and all that are off, and then compare them with a fluorescent. So this might be the fluorescent. But the trouble is those are at different times, aren't they? No. I beg your pardon, at the same time. So, background, blah blah blah. So there is a change, quite a large